So multiple alignments, as I said, it induces. There's implicitly in a multiple sequence alignment, we have pairwise alignments. By considering each pair of rows, we can see the pairwise alignment between those sequences indicated by those rows. And so it has an example between three sequences x, y, z. This multiple sequence alignment induces these pairwise alignments between rows x, y, x, z, and y, z. Now, let's consider the inverse problem. If we are given, okay, a given multiple sequence alignment may induce this. Now, if we know that we can compute these efficiently, each of these k-square pairwise alignments can be computed in n square time. If we have these things, can we go back from these individual pairwise alignments to build a multiple sequence alignment? And here are three arbitrary pairwise alignments which are optimum. Each of these pairs are optimum. Now, can we construct a multiple alignment that is going to induce them? And the answer is already said, it's not always. It's sometimes pairwise alignments. If you're combining them together, you cannot just put all these alignments on top of each other because there are going to be inconsistencies in between them. And from an optimal alignment, from an optimal multiple alignment, the pairwise alignments induced by them are not necessarily optimal pairwise alignments. So here's an example from the book which tries to align, sorry, the fonts are too small. I'm going to draw it on the board by, okay. So here's the alignment between AATT, TTGG, and AAGG. Imagine we try to align these three things. Here and okay, we try to align these. Here, if the alignments were like this, and TTGG. So this is the pairwise alignment between these two. So actually, no, this example is for the one we can do. Let's assume this one was GGAA. Okay. So if we align AATT with GGAA, this is the alignment between these two. And TTGG versus GGAA. Okay. Now, here we have three alignments, pairwise optimal between all of them. Now, if we try to combine these three alignments into a single alignment, we are going to see we will have inconsistencies. It's like this. Let's see if you want to first combine these two alignments, this alignment with this alignment. Okay, if you're going to combine this alignment with this alignment, sorry, so we have AAT, TTG, AAT, GGA, and yes. So if you're going to combine this one with this one, this is the shared sequence between these two alignments. What we are going to have is that if we align this to each other, these AAs are aligned with each other. So AAs like this, and GG, sorry, this is AAGG. What I'm going to do is, yeah, AATT, right? So if you combine these two alignments, this is what you're going to get. TTGG, GGAA, AATT. Now, as you can see, this alignment is conflicting with this alignment, because in this alignment the TTs are aligned. So there's no way you can put the first alignment, the optimal alignment, there's no way you can align these TTs. They are going to be in different parts of the sequence. So if you try to put AATT to align with TTG, you cannot do that. You cannot have two copies of the same alignment. So this AATT, which is this sequence, you cannot put it here and then put it here, okay? Because you decided by combining these two alignments, you decided to put AATT to the right part of this multiple sequence alignment. But this alignment says that it should appear as at the first part of this multiple alignment. So these two things are in conflict with each other. So multiple sequence pairwise alignments cannot always be combined to produce a multiple alignment. And given a multiple sequence alignment, we can also talk about the consensus string. The consensus string is the majority in a column. The majority of the the majority of the nucleotides or amino acids in a column denotes the consensus nucleotide at that column. By combining all these consensus nucleotides, we can have the consensus sequence, which is like the sequence most likely indicated by each of the sequences. Now, we also have seen the profile representation of family by using frequencies of each amino acids, each nucleotides in a column. And we also said that we can align sequence against a profile. We have seen how we align a sequence against a profile by maintaining these profiles for each pairwise alignment, sometimes by aligning a profile against a sequence or by aligning two profiles. We can actually either combine two different alignments or combine a sequence with a previous alignment. Okay. We can have a combined alignment by aligning two profiles. We have seen this at the beginning of just before the position-specific scoring matrices subject. Now, here is one approach. We can do multiple alignments by using this greedy heuristic. This greedy heuristic says that given a multiple sequence alignment, given a number of sequences, k sequences, choose among these k sequences, choose the most similar pair of sequences and combine them into a profile. Doing this will reduce the number of your sequences from k to k minus 1, okay? Because that profile is like a single sequence. Instead of amino acids at each column, we just have a percentages of amino acids, but it's like again, it's going to act like a single sequence. So then this greedy approach, starting from k sequences, by choosing the most similar pair and aligning them and removing both of them from the set and inserting their alignment into the set, we are going to have k minus 1 sequences left in our alignment. And by repeating this k minus 1 times, at the end we are going to left with a single sequence, which is going to be the alignment of all these k sequences. And this single profile, this single sequence is going to represent the multiple sequence alignment. So this is a greedy heuristic in which it tries to, at each time, it chooses the most similar pair of sequences among the set. This is the greedy strategy. At each iteration, at each step, choosing the most similar pair of sequences. Now, what may be the disadvantage of such an approach? When does the greedy fail? Okay, let's think about if we are given k sequences, when will this greedy approach is going to fail? Can you think of a counterexample? Think of a certain family of sequences, a set of sequences, in which this greedy approach probably is not going to work very well. So this could be an exam question, for example. This could be a midterm exam question. So when does this greedy approach is not going to work well?
Maybe a similar sequence better occurred
Okay, if we are given k sequences, if we have a pattern here, this pattern is occurring in, and this pattern is occurring in many times within the sequence you're saying. Okay. And variable number of times maybe between.
A part of a big pattern. A similar pattern. Maybe a part of a big pattern. That must be somewhere specific. But aligns the first one because of greedy.
Oh, so in the first, so you say that. Okay, let me try to understand. So we have a big pattern. Does this big pattern exist in one of these sequences, in the K? In K sequences, does this, do we observe this big pattern in a number of, in a set of them?
I mean, it's a pattern that all the sequences must match, but before that, a small pattern that the big pattern contains.
Okay. But now we have this pattern, but this pattern should be part of some sequence because we are not doing a pattern search here. What we are doing is we are doing multiple sequence alignments. So you are given k sequences. Now you need to tell me you need to tell me information about these sequences. For example, the first two sequences have this pattern, the complete pattern, but the other two sequences have the subset of this pattern. You should, your explanation should be something like that. So, do you, is it the same? Is it what you're saying? So maybe these two sequences, they have the whole pattern, but the other contain a small part of this pattern, which is a subset of the big pattern. So. In this case, what will happen is that, for example, the most similar sequences in the greedy approach, the first sequences are going to be these two sequences, okay? Because since they are having a high similarity in this pattern region, probably these two are the first pair of sequences that is going to receive the highest score, and we are going to align them first. So the pattern region is going to be aligned correctly. And at the next phase, we are going to be looking for the most similar sequence between this one and these and between these three sequences. And between these three sequences, maybe these two are going to be the next best pair. And we are going to align them and put an alignment in between them. And we are going to replace it with their alignment at the end. So still it seems it's going to work. I cannot see whether there will be a problem here. Yes?
Greedy approach can fail how it decides the similar sequences at the beginning.
Okay. Okay, so if it can fail if there is not enough similarity between a pair of sequences. It will be forced to align pairs of sequences which are not very similar to each other. But it may be a problem of the general multiple sequence alignment. I mean, this is a problem actually. You're right, this is a problem, but it may be a problem of the whole multiple sequence alignment algorithms, because if there are no pairs of similar sequences, the others may also have difficulties. I mean, imagine you're aligning something, even a pair of sequences are not sharing enough similarity. So it probably means that, this observation probably means that your sequences are unrelated, all of them. There is no relation between them. Any other ideas? But these are all good ideas. I mean, even this one is not a bad idea. Just it may tell you. I mean, there's something here at this In this greedy approach, what we have here is at the second step, we try to align these two together. But maybe if we align this one, it may be found that this one is found similar to this one, and which may cause an incorrect positioning of this in this alignment. But if we did this alignment after we aligned these two, we would maybe have a more strong evidence to put these two together. But aligning one of them to this pattern, we may have multiple options to put the single pattern in this larger pattern. But if we have already previously aligned these two together, we will have a stronger evidence about where to put this exact. I mean, combining these two will give us a better idea maybe to find this exact location in this larger pattern. Okay, I mean, this is just one idea.
Similar patterns are one of them is the first beginning of the sequence, and the second one will be in the last of the double sequence. The greedy approach will not operate normally. I mean, it will dismiss some of the other similarities between them. So if the greedy approach starts, if we have multiple sequence alignments and the similarities are from the different part of the sequences which are nearly opposite of each other, the alignment will not operate.
Okay. Yeah. So I mean, that's also true. So the greedy approach, if you're thinking about cases where when you're thinking about cases where it's going to fail, you should. I mean. Disadvantages of other multiple sequence alignment approaches also apply to the greedy approach. I mean, if what you decide early, after you make a decision, I'm going to align these two sequences, if this decision causes incorrect parts of the sequences to be aligned to each other, which is going to affect the rest of the aligned sequences, so this will be the disadvantage of the greedy approach. So when you're deciding to make an alignment and this alignment causes an incorrect decision, like another example, this is the example Sasan is talking about. So imagine we have again 4 sequences. Now, there is a certain region here, and part of that region appears here in this sequence, okay? And in the others, so these parts are similar regions. So if we have something like this, okay, because this region is matching, and also there may be the same region here, but with some mutations, with some changes here, okay? This region A, is repeated in this sequence, and somehow this first part resembles more to this part. And since this is a longer part, it may receive a higher score compared to the other pairs. And this decision is going to have us to align this part to this part here. So our alignment is going to be something like this. Although there is a weaker signal of the same parts and a strong signal but a smaller region that matches, we will have this alignment by choosing to align this one and this one, after choosing to align this one and this one. And this will cause maybe to align these two regions. They are going to be aligned here also, and we will lose the fact that actually this region is also similar, belongs to this region. So this incorrect choice at the greedy decision will allow us, will actually cause us to miss situations like this. But there may be more than one such cases you can think about. I just want to elaborate on what is multiple sequence alignment doing. So at each step, we are doing a certain decision, and we are fixing it. Here is another greedy approach. An example. We have 4 sequences. In these 4 sequences, there are 6 possible alignments between them. We compare each of them, and we see this has the highest score, so we use this alignment, combine them. The combination after this combined sequences of the alignment is represented as a profile like this. It's a GTC, and the 4th position is T or A. Then G, 5th position is A or C, and I have A. Actually, this is, so GTC, TA, G, and A. Actually, we are missing the final A here. Okay, so this is a typo. You should just erase this A. Now we have a new set of 3 sequences. This is our, we have a profile and 2 sequences. We align all 3 of them. Again, we look at all the alignments between these 3 sequences. One of them is a profile actually, and pick the one with the highest similarity. We combine them. We are going to be left with 2 sequences or 2 profiles, and then we are going to combine them to get the final multiple alignment. So this is how greedy works. And greedy algorithm is a progressive alignment strategy in which we build a multiple alignment by iteratively combining pairwise alignments. This is what progressive alignment stands for. If you see a paper, for example, that says a progressive alignment strategy for multiple sequence alignment, this is what it means. It means it combines pairwise sequence alignments to build multiple sequence alignment. And star alignment is one such technique. I mentioned star alignment. So in star alignment, we pick a central sequence. We select one of the sequences out of these K sequences as the center. It's also called the star of the alignment, the center of the star alignment. And for each sequence, for each other sequence, which is not the star sequence, the central sequence, we perform a dynamic programming optimal alignment. And we combine these alignments into a final alignment. In order to choose the center, first we do case all pairwise alignments are computed, and then we choose the central sequence which maximizes this total score. So it's like this. We ask everybody in this class, who are your friends? Okay? If I do it for everybody, I'm going to be asking, if there are n students in this class, I'm going to be doing n square questions. Okay, who are your friends? Actually, I'm asking n questions to n people, but each of these students is going to tell me whether this student is a friend or this student is not a friend. So each student is going to give me n minus 1 answers, right? It's going to say, this is my friend, this is not my friend, this is my friend, this is not my friend. So for each student, what I have is, by accumulating, by analyzing these n minus 1 answers of each student, I can find which student has the maximum number of friends. Okay, so this is what we do here. After computing all the n square alignments, I ask each sequence, each I here, for each sequence xi is asked about, what is your score to this jade sequence? What is your score to other jade sequence? What is your score to all other sequences? We sum up all these scores, and the sequence I, which has this maximum total score, is going to be our central sequence. And here's an example. Here S2 is our central sequence, which is MKE. And after we have this central sequence, we already have dynamic programming. Actually, when we are finding the central sequence, we have already performed all the alignments between all pairs. We can reuse this alignments when we are building the multiple sequence alignments. For example, the optimal alignment between MKE and MPE was this. And the optimal alignment between MKE and MSKE is this. And between MKE and SKE was this. So we can combine all of them by putting these alignments on top of them. So the idea of star alignment is that if you choose a central pivot sequence and you use the alignments to that sequence, you can just write all the alignments on top of each other. There will be no inconsistency. If you choose a single pivot sequence, you can then combine all the pairwise alignments to perform a to form a multiple sequence alignment. There will be no inconsistencies because you have a central reference sequence. Okay? You cannot, for example, in this example, we had this triangle, okay? The inconsistency arises from the fact that we did not have a single pivot sequence. For example, if we choose one of them as the pivot sequence, after we combine these two alignments, we had a multiple alignment. I mean, in that multiple alignment, these T regions were not aligned, but these T regions that were aligned is not an alignment between the pivot sequence and, I mean, if we choose a single pivot, we will not have any inconsistencies. That pivot is going to tell us where the other amino acids and the other letters are going to appear. Okay, so in this example, when we choose MKE as the pivot, so this is MPE, alignment of MPE to MKE is this. And if we add MSKE to this alignment, MSKE sees that this MKE has a gap in this region. So this gap, putting gap in this region, is going to induce a gap in the previous alignment because this previous alignment says that these are matched to each other. It doesn't say anything about gaps because in alignments we do not have two gaps in an alignment. But putting this S in the middle is going to introduce a gap in this MKE, and which is we are going to put this gap here in order to be consistent, in order to continue this consistent matching between MPE and MKE. And SKE, between the alignment between MKE and SKE, it can easily be introduced in the alignment as well. And at the end, we are going to have this. So by choosing a single pivot, we will not have inconsistencies when combining these alignments. So that's the main idea of star alignment. And its overall cost is k square n square. As you can see, in polynomial time, we can build a multiple alignment. But here, we cannot guarantee, and the disadvantage of star alignment is that if your center sequence is not similar enough to all of the sequences, your alignments may be wrong. Okay? If, for example, imagine I gave you k sequences in which there are two groups, two main groups in this family. For example, I give you a superfamily of sequences, and there are two families in this superfamily. Each one of them has a single star. But in this algorithm, you need to choose a single star, and therefore this single star is going to be a good representative of one family, but it's not going to be a very good representative of the other family. So the alignments with this center to all the family members in this other family is going to be bad alignments, and we are going to be accumulating using them to build the multiple sequence alignment. So the disadvantage of star alignment is this. It just picks a single center and tries to, which the main assumption in star alignment is there is such a central sequence. If in your actual sequences, there is no such central single sequence which is close to everybody, probably star alignment is not a good way to go. Okay? If there are groups of subsimilar groups of similar subgroups of similar sequences in your set, then maybe the better way to do is choose stars choose 3 stars maybe, use star alignment in each of these 3 groups, then try to combine these 3 alignments into a single alignment. That may be one strategy. And actually, this is what Clustal W does, something similar. The guide tree that we are talking about, if there are multiple groups of similar subsets, it aligns them separately first, and then it tries to combine them by going through a tree. So here's the Clustal W. It's one of the most popular alignment tools. As I said, T-Coffee and Muscle are also gaining popularity. And W stands for weighted alignment. Here, different parts of the alignment are weighted differently based on conservation. And there's a 3-step process. It first constructs pairwise alignments between all pairs of sequences. That's also what this first step is the same first step as the star alignment, right? The star alignment also first does a it computes the all-to-all pairwise alignment. If you have n sequences, n square pairwise alignments are computed. And out of these pairwise alignments, what star alignment was doing was, by using these alignments, it was choosing a single center. Now, what Clustal W does differently is that it uses the results of these pairwise alignments to build a guide tree by using the neighbor joining method, which we are going to see next week. So this neighbor joining method builds phylogenetic tree, builds a relationship tree, similar to a phylogenetic tree, between these sequences. Which sequences are most similar to each other, which you immediately, by looking at this tree, you immediately see groups of, subgroups of similar sequences. And this guide tree is then used to guide a progressive alignment. And the sequences are aligned progressively according to the branching order in the guide tree. So that's, here's an example. The first step, we do a pairwise alignment. Okay, here's our similarity measure, for example. You can use, when you are, after you build your pairwise sequence alignments, you can either use the score, you can compute maybe a certain distance, or you can use percent identity, for example, as similarity. So you can use several different measures after you do the alignment. Here, this one shows the percent identities. And if we look at this, we see that V1 and V3 are the most similar, okay? 87% identity. So probably we should start with V1 and V3, but then we should combine V4 to that. So we need to build a guide tree after this. Okay, the guide tree is using the similarity matrix, or it may also use, we may also, instead of these similarities, we may use a distance measure. Distance measure may be computed, it's the inverse of this similarity. We may compute the edit distance, for example, between sequences. And so this was the similarity. And the guide tree is like this. As you can see, as we guessed, V1, V3 are aligned first, then V4 is added to that, and V2 is added at last. So if we first align these two, add V4 and add V2 to this. And for this particular example, probably the greedy strategy will exactly do the same alignment. Okay? If you do the greedy technique, the greedy again is going to start with V1, V3. Okay? Then what we do is, at the greedy strategy, at the next step, we again need to do n-square comparisons to compare the result of this V1 tree against the other two. Okay? The one difference in the greedy approach is that at each step, we are doing n-square alignments. At each step, I mean, this is not exactly n-square, but at the first step, we are doing k-square alignments. At the second step, we have k-1 sequences at the greedy approach. So we are comparing all k-1 sequences again with respect to everybody. So it's k-1 square, then k-2 square, k-3 square. So at each step of the greedy approach, we compare all the pairwise sequences to choose which one is the most similar to each other. Okay, after we have this V1, V3 aligned, we put their alignment to the set, and we check whether this alignment is close to the other ones as well. But this one does not do that, because this tree is built from this n-square alignments, and after we have this tree, we do not do any intermediate alignments during this step. We are not again comparing the result of V1 tree to everybody. We don't do that in guide tree, because the guide tree immediately tells us that after you align V1 tree, just align this result with V4. This fact, the next step, what we are going to do in the next step is known from the beginning. Okay? After you have the guide tree, you know each of your steps. But in the greedy approach, at the beginning of each iteration, you don't know anything about what you're going to do in the next step. At the beginning of each iteration in the greedy algorithm, you make a new decision by comparing all the pairs of sequences in your current set. By comparing all of them, you pick the most similar ones, and you do this computation at each step of the greedy approach. So in terms of computational complexity, greedy also has a disadvantage. And this, after we calculate this, so this is the progressive alignment here. The progressive alignment starts by aligning the most similar sequences and following the guide tree. It adds the existing. And here's an example result of Clustal W alignment. To give some information to the user, actually it could have been good if we had these columns colored differently, which indicates conserved regions, conserved blocks, because reading an alignment like this is not very easy. It's difficult to see immediately which parts are conserved, right? So to assist in such reading the final alignment, Clustal W provides, as the last column here, provides some information. For example, dots and stars show how well conserved a column is. We have a star here. Star shows an exact conserved column with all the same. By looking at these stars, we see the conserved regions. And dots, somewhat conserved, and double dots, better conserved. So it has these three levels, dots, columns, and stars, which show how well a conserved column is. Okay, this is just for visual representation of the multiple sequence alignment. Here's another example of Clustal W. This time we have a distance matrix instead of a similarity matrix. As I said, distance and similarity are same concepts. One of them is the inverse of the other. In the first similarity one, you are looking for the maximum similarity when you're choosing. If you have distances, you will be choosing minimum distance. So since they're inverse, minimum distance is equal to maximum similarity. So here the first thing, sequences to compare are the S2 and S4. And also S3 is close to S1. Maybe we are going to have a different guide tree, which is a balanced tree. Unlike the first example, this is a balanced tree. We first S1, S3, S2, S4, and this is what we have. Okay, this is how Clustal W works. There are other progressive alignment approaches like pile-up. And here, problems with progressive alignments is that it depends on pairwise alignments. If all sequences are very distantly related, we have much higher likelihood of errors. And the scoring matrices and penalties, they have great effect on the results. Choosing them appropriately is very important. And here's an example of the limitations of the progressive strategy, in which if you do an error in the beginning of the alignment, that error is going to propagate until the last. So when you do an alignment, in this progressive alignment, you align a pair and you make this decision, you never go back and correct that decision. After maybe you see at the final alignment, you can say, oh, okay, I did this matching incorrectly, but it will be too late. You will not be able to go back and correct it, because if you want to do that, it's going to cost you some computational time. So progressive alignments do not do that. But there are iterative algorithms in which after the multiple alignment is found, given a multiple alignment, it looks for such iterative algorithms, looks for things like this. If I change this part of the alignment, will I get a better alignment? So iteratively, they try to modify certain parts of the given multiple alignment to make it a better alignment. So they, in certain iterations, in a number of iterations, by making random changes in the alignment, they see whether they can get a better score or not. If they can get a better score, they make these changes. So this example, this is the guide tree, which tells us that the first thing to align are these two sequences. And here, these are my four sequences, okay? The fat cat, Garfield, the very fast cat, Garfield, the fast cat, and Garfield, the last fat cat. Okay, so when we align this, you can see here, cat is something that should be aligned together. Okay, but here in this first, the Garfield, the fast cat, and Garfield, the last fat cat, in this alignment, the optimal alignment, we choose this last and fast are aligned to each other because of the shared word S here, and therefore by allowing one mismatch, again we align fat with a cat. And this final cat is not aligned to anybody. It's aligned against gaps. Okay? In this case, the wrong choice of aligning this fat with a cat here propagates until the end of the alignment. So we are going to have a wrong alignment. But if you see all of these sequences together, you can immediately do the actual alignment saying that cats should be aligned and fat and fast should be aligned. The mutation here is that fat, we have inserted an S there to make fat a fast, okay? And last here is also something that is inserted. It should be, I mean, this fast should be aligned to this one, and this very is also something that is inserted. So the correct alignment can be found after we see all of the sequences at the end of the alignment. So iterative refinement is by looking at these alignments and iteratively making changes. And there are different ways to evaluate multiple alignments, but I'm going to stop here. And only thing we have left in this set of slides is the evaluation of multiple alignments. I'm going to finish that in our first lecture next week. And in our second lecture on Friday, we are going to have the midterm. Okay? So the midterm is going to cover until the end of the multiple sequence alignments. So this evaluation of multiple alignments, the subjects that we are going to cover on Thursday are also going to be included in the midterm. Okay? So the evaluation of multiple sequence alignment algorithms. Midterm is going to be in class at the same time. But I guess I have reserved BMB1. It may be in BMB1, but if I'm going to check if BMB1 is full, we may have our midterm here. Here and BMB5, we can use 2 rooms, or it will be in BMB1. I'm going to check for that, but it's going to be in class. So if you just come to your regular class on Friday, you'll be able to have your midterm exam.